Hi everyone, greetings of the day. I'm Dr. B. Ravi Chandra, Associate Professor in the Department of ESE in G Pullaiah College of Engineering and Technology. Today I'm here to discuss about another topics which is nothing but designing of IIR filter by approximation of derivatives on impulse invariant and bilinear transformation method. If we recall the classes which we have seen in the last class we have seen some two types of techniques. One is Chebyshev filter and another one is Butterworth filter, where what we have done in that particular lecture with by using the two topics, one is Butterworth and Chebyshev filter, we have designed the transfer function of analog filter. Okay, we have designed the transfer function of analog filter, that is H of S, and then after that, by using this particular three techniques, what we are going to do, we are converting that analog filters, that is transfer function of analog filters, into digital filters. So if you see that the difference between IIR and FIR filter is used to convert the filters, analog filters, directly into digital filters. But coming to this IIR filter, what happens here? Some small process, a little process will be happens where first of all we are going to design the transfer function of analog filter by using two techniques we have discussed in the last lectures, that is Butterworth and Chebyshev filter. Fine. So after designing that H of S transfer function of analog filters, now by using these three different types of techniques, that transfer function of analog filters is going to convert into digital filters. This is the concept. So now we will see what is the steps involved in designing the or in converting the analog filters into digital filters. So the contents which what I am going to discuss in this particular lecture. So how we are going to design the digital IR filters from analog filters. Okay, that is analog filters where we have seen the transfer function H of S of the analog filters. Now here we are converting this analog filters H of S transfer function of analog filters into digital filters by these three techniques. One is approximation of derivatives, second one is impulse invariant transformation, and third one is bilinear transformation. So in this lecture we will see the steps how we are going to design, and at the end of the session we will take each one example, and that we will get a clarity that how we are going to converting this transfer function of analog filter into digital filter. Okay, now what are these three main, how these three methods are going to convert the analog filters to digital ones? First one is approximation of derivatives. Please observe this heading, approximation of derivatives. So what happens here, this method helps to convert the continuous signals, that is the analog signals, to convert the continuous signals into digital ones, by approximating how changes happen over time. Okay, how changes happens over time, how this particular method is going to convert these continuous time signals into digital signals. Okay, now coming to the second one, impulse invariant method. So this method makes sure the behavior of the filter in the digital world matches the original signal. So it makes sure, that means you please observe this word impulse. That means this method makes sure the behavior of the filter, that is the impulse behavior of the filter, the system, and what happens, the output which is formed at the destination side, that is the digital board, should matches. Why? Because the impulse of the digital board should matches the input signal, impulse of the input signal, that is original analog filter. I think you got the point. The name itself telling impulse of the output, that is digital world, impulse of the digital system or the digital filter at the output side should matches the original analog filter at the input side. The impulse should be matched. So the output of the impulse digital filter should match to the input impulse analog filter, so that this particular invariant method will be used here. Now third one, bilinear transformation. So this method is commonly used because it avoids some problems that can arise in other methods like distortion. So this is the main method. What are the drawbacks that is present in the approximation method and impulse invariance method? Whatever the drawbacks that is present in both methods, that is overcome by this particular method, which is bilinear transformation method. That means So it avoids the problems which is arised in previous methods, like distortions at the high frequencies. So these drawbacks will be overcome by the bilinear transformation. So whatever it may be, the three methods are used to convert an analog filter into digital filter according to their operation. Okay, so these are the three methods. Let's see what is how the designing of digital filters from analog filters happens. Just firstly we will recall the things what happens here. When the designing digital filters, that is, we are designing the digital filters, how? By converting the analog filters. Okay na? So filters which are using in the digital systems, so how it is forming? By converting the analog filters, that is the filters which are in the analog forms like radios and TVs. Now the conversion happens from analog to digital filters. So for the conversion to be successful, it should satisfy these two conditions. Be careful, these are the two conditions which it should satisfy for conversion of the analog filters into digital filters. The first one is, see here, the j omega axis, which represents the frequency in the analog world. Okay, the j omega axis in the S plane. Just observe this particular diagram. The j omega axis in the S plane must match up with the unit circle in the Z plane. So must match with the unit circle in the Z plane. So we have two planes, one is S plane and Z plane. So here the j omega axis which is present in particular S plane should matches with the unit axis, should match up with the unit circle that is present in the Z plane. So whatever it is present in the S plane, it should match with the unit circle that is in the Z plane. So according to this only, that ensures that there is a clear relationship between this S plane and Z plane. So this is the first condition we should satisfy for the conversion of analog to digital. And the second one, see here, same. The left half of the S plane, see here, which is nothing but the analog, should map to the inside. See, I have drawn this, should map to the inside of the unit circle in the Z plane. So if it is mapped, then only we can say that the particular analog filter can be converted into digital filter, or a stable analog filter can be converted into a stable digital filter. Thus the systems will be, filters will be stable. So for this conversion, we should satisfy this, we should follow these particular two conditions, so that we can easily convert the analog filters into digital filters. Okay, see here. So for this purpose, so according to these two criteria, let's discuss the first topic, which is approximation of derivatives. Then approximation of derivation. For that, what we are going to do? This method approximate the differential operation in an analog filter by an equivalence difference operation. Difference equation we are considering here. So for that, what I am taking here, the equation for the derivative, difference back equation I am considering. So for that, if I do the derivative, that is d by dt of y of t. So d by dt of y of t at t is equal to nt. So I am going to get the equation which is a derivative of the equation. So this is the derivative of the approximation equation. This, so by doing the derivatives of the differential equation, I am going to get this one. So here t is the sampling interval and y of nt is the sampled signal at the nth interval. Now what happens after that? System function in the analog domain. So the system function of the analog differential operator is, we know that h of s is equal to s. Why? Because we have already designed this h of s, which is the transfer function of the analog filter by using the two methods, Chebyshev and Butterworth filter. So, and we know that h of s already it will be given in the problem. So this represents the analog form of the system function. Now after getting this, we need to convert into digital domain. We got there h of s is equal to s, which is the analog formation of the system function. Now we need to convert that into digital domain, that is h of s into h of z. So we need to convert from h of s into h of z. So for that, what we need to do? We should substitute s in the place of s 1 minus z inverse by t. So by substituting this, we are going to get, we are substituting in the place of s, I am substituting 1 minus z inverse by t to the power of k. So here this is the higher order derivative. So for a higher order derivative, the corresponding frequency domain relationship is this one. So with this particular condition, the continuous time signals can be converted into the discretized time signals. So what a simple thing is, whatever the transfer function we are getting in the problem, in the transfer function, in the place of s, we need to substitute 1 minus z inverse by t, so that h of s will be converted into h of z. So simple thing. It's very simple when derivative. So after doing the derivative, whatever the transfer function we are getting, just we substituting the s. In the place of s, I am just substituting 1 minus z inverse by t. So we will have a smaller problem. See here, just the analog filter can be converted into the corresponding digital filter. How? By substituting s tends to, in the place of s, 1 minus z inverse by t, where we need to substitute? We need to substitute in the transfer function of the analog filter. So after substituting this, it will be converted into h of z. Clear? See here. So how we are going to convert? Just by substituting in the place of s, that is 1 minus z inverse. Just we will take one problem. What is saying? Convert an analog bandpass filter with the system function. See here, I told you, they will give directly the transfer function of the analog system. Okay, so transfer function they have given, that is HA of s is equal to 1 by s plus 0.1 whole square plus 9. Okay, now what he is asking, please convert this into digital infinite impulse response, DIIR filter, using the derivative substitution method. So simply they have given the analog filter which is HA of s. Just what we need to do, we need to substitute for the digitalized digital conversion, in the place of s, we need to substitute 1 minus z inverse by t. So what is the equation? S plus 0.1 whole square. So where we are substituting? We are substituting in the place of s 1 minus z inverse by t. So after substituting and simplifying that particular equation, we are going to get this one, that is t square by 1 plus 0.270 plus 0.917 square into 1 by 1 plus 0.270 plus 9.017 square into z to the power of minus 2. After doing the simplification, we are going to get this the equation. Now here, for the stability, what we told, according to the conditions, we have studied two conditions. In the second condition, the conversion should be stable for the analog filter as well as the digital filter. That's why pole location. For the stability, if the system should be stable, the pole should be lies within the circle, within the unit circle or within the z plane. Then only we can say that the filter is in stable condition. For that, what we are going to do? We are taking one condition, t less than or equal to 0.1. So in the place of t, what we am doing? I am just substituting 0.1 in the place of t. Why? Because he said the condition is t less than or equal to 0.1 for poles near the unit circle. That means if I want to say the given filter is the formed filter is in stable condition, when we will say that when the poles should lies in the circle or nearer to the circle. So for this purpose, to show that filter is in stable condition, we need to take this particular t less than or equal to 0.1. So after substituting, replacing the value in the formed equation, what I got here, the magnitude I got is 0.949, which is nearer to the 1, and the phase is plus or minus 16.5 degrees. So according to this particular problem, we can say that the given transfer function of the analog filter is lying nearer to the unit circle of the z plane, so that here we can easily convert this analog filter into digital filter. This is a very simple problem where just we need to substituting in the place of s 1 minus z inverse by t. So after that, we need to know the location of the poles. For that, we are taking one condition, t less than or equal to 0.1, substituting the value of t in the place of formed equation. Then we can come to know that the poles are lying within the circle or nearer to the circle. So according to this particular value, we can confirm whether the converted filter is a stable filter or not. So this is the first method, how we are going to convert the transfer function of the analog filter into digital filter. Now coming to the second one. Okay, before going to the second, that is impulse invariant method or bilinear transformation, we can see some different types of drawbacks that is present in the approximation of derivatives. What are the drawbacks? Errors in approximation, that is the process of approximating while doing the derivatives, some small errors causing the digital filter to behave different from the analog filter. While we are doing the derivation of that particular equation, what happens? Some small errors will be occur where the behavior of the output, which is digital one, will be different to that of input, which is analog one. So that is the first error. And instability. Just now we have seen the problem. where if it is slightly nearer to the circle, not a problem. If it is far from the circle or unit circle, the stability will be down. So if the sampling rate is too low, while we are doing the sampling rate, if it is too low, the filter may become unstable or produces unwanted signal, that is noise will be formed. Unwanted oscillation means aliasing something will be formed. So that's why instability is also one of the main cause, main drawback. Frequency mismatch. So the digital filters frequency response may not match the analog filters, causing distortions in the signal. Matching will be somewhat different. So increased complexity. We are doing the higher order derivatives. So the name itself telling approximation of derivatives. We are doing the higher order derivatives which lead to more complexity equations. Okay, as you know that while doing the derivatives, it is somewhat very complexity while doing the derivative part. So because of that also the complexity will be increased and it will be one of the drawback. As usual, we seen here frequency matching. What happens here? Aliasing will also affect the frequency overlapping with the another frequency. That is also one of the main cause drawback in the approximation of the derivatives. Next one, precision loss. Digital system have limited precision which can cause small rounding errors that accumulate over time. So some different types of precision losses will also occur in the approximation of the derivatives. So these are the main drawbacks that is present while we are converting the analog filter into digital filter. So to overcome this, another method has been introduced which is impulse invariant method. So let's see what are the steps that involves. So what we need to do, whatever the transfer function we got with the help of two methods, one is Chebyshev method and Butterworth method. From here, by using the impulse invariant method, we are converting that into H object. So for that one, we need to do first step. For the given specification, in the problem we will get some different types of specifications. We need to find out the value of HA of S. Okay, the transfer function of the analog filter. By substituting all the specifications in the transfer function of the analog filter, we will get the value, that is HA of S will be found. So after that, the t seconds, that is sampling rate, we will get some value which is related to the sampling rate t seconds, that is substituted in the formed equation which is done in the first step. After that, express the analog filter transfer function as the sum of single pole filters. Like, see here, we formed one equation which is the transfer function of the analog filter. Here we need to check the transfer function of the sum of single poles. For example, if I get n is equal to 2 here, that means 2 poles I got. So how the equation I can write? H of S is equal to, so k is equal to 1 to 2. Why? Because n is equal to 2 na. So what I can write here? C1 by S minus P1 plus, what he told, as the sum of single pole filters. How many poles I got here? 2 poles. For example, if I get 2 poles, it should be sum C1 by S minus P1, C2 by S minus P2. So in the third step, we are going to summate the analog filter transfer function of the single pole filters. In the fourth step, compute that summation into the digital form. That is, we are converting that H of S into H of Z by using this particular formula. We will see, you will get a clarity while we are doing the problem here. So by using this, we are going to convert that analog transfer function into digital. Finally, for high sampling rates, if we get any high sampling rates, we are going to get this equation. Up to now, up to fourth step, it will be maximum, it will be completed. If there is some high sampling rates, then what happens? This is the equation we are going to use. Okay, so these are the 4 steps which is used to convert the digital filters into analog filters into digital one. Now we will see one problem, taking one problem. So we got the transfer function of the analog filter H of S is equal to 2 by S plus 1 into S plus 2. So determine the H of Z. He is asking to convert that into H of Z by using the impulse invariance method, and you can see here the sampling rate capital T is equal to 1 second they have given. So in the first step, what we are going to do, we need to find out the values of H of S. So for that, what I am doing, I am taking the partial fraction. See here, I got 2 by S plus 1 into S plus 2. For that, what I am doing, with the help of partial fraction method, I am rearranging that particular equation in the form of H of S is equal to A by S plus 1 plus B by S plus 2 by using the partial fraction method. So how we need to find out the value of capital A and capital B. For that, first what I am substituting, capital E is equal to minus 1, so that I got the value 2. See here, I substituted the value capital A, that is s tends to minus way. In the place of to find out the value of a, I am substituting s is equal to minus 1. So after that I got a is equal to 2. Similarly, to find out the value of b, what I am going to do, I am substituting s is equal to minus 2. Okay, so by doing that I got the value b value minus 2. So after getting that value, see here in the third one, using the impulse invariance technique, we have h of s is equal to, just now we have seen the steps, summation k is equal to 1 to n ck by s minus pk. So how many poles we got here? We got 2 poles. Okay, s plus 1 into s plus 2. So p1 is equal to minus 1 and p2 is equal to minus 2. See here, 2 poles I got, s is equal to minus 1, s is equal to minus 2. So that's what, p1 is equal to minus 1, p2 is equal to minus 2. And what are the, c1 is equal to 2 and c2 is equal to minus 2 I got here. So there are 2 poles p1 and p2. So with the help of that particular, what I am going to do here, I am summating. So how many poles I got here? 2 poles. See here, h of z is equal to, I am writing one step here. See, h of z is equal to 2 poles I got. So instead of that, I am writing c1 by 1 minus e power p1t z power minus 1 plus c2 divided by 1 minus e power p2t into z power minus 1. So this is summation. I am summing the 2 poles. So taken summation, I summated the 2 poles. So what is the value of c1? c1 is equal to 2. What is the value of p1? Here p1 is equal to minus 1. That's why, see here, minus 1. So instead of p1, I am writing there minus 1. So 1 minus e power minus t, z power minus 1. First summation. Second one, what is c2? c2 is equal to minus 2. That's why instead of place, I am writing minus 1 in 2 divided by 1 minus 2 power p2. What is the value of p2? Minus 2. So e power minus 2t into z power minus 1. So, and what is the value we have given in the problem? T is equal to 1 second. So substituting the value t is equal to 1 second and simplifying that, this is the finalized equation what I got, which is nothing but h of z. So what we have done? Just we have taken the h of s and we have done the summation of 2 poles and we have converted that into h of z, which is converted in digital form. Analog form, the transfer function of analog form is converted into digital form by using the 4 steps that involves in the impulse invariance method. So this is the small problem which is related to the impulse invariant method, how to design the IIR filter. Okay. Now, finally the last method. So the method of designing this IIR analog filter into digital filter, we are using another method which is bilinear transformation method. So why we are going with this means, the method of filter designed by impulse invariance suffers from aliasing. This is one of the drawback that is present in the previous method what we have discussed, which is impulse invariant method. It suffers from aliasing effect. Hence, in order to overcome this drawback, we are going with the bilinear transformation method. So bilinear transformation method is a mapping from analog S plane to digital Z plane. First mapping of the analog S plane to digital Z plane, then the conversion maps analog poles to digital poles and analog zeros to digital zeros. Thus all poles and zeros are mapped. The main agenda is that to overcome the aliasing effect, they are concentrating both on poles and zeros, and that poles and zeros in the both S and Z plane should be mapped with each other. So that is the main agenda present in the bilinear transformation. So we will see the step. First one, we are giving the some specifications. Find the pre-wrapping, that is angular frequencies omega 2 by t tan of omega by 2, and we are going to find out the 2 frequencies. One is passband frequencies omega p and stop band frequencies omega s by using these 2 formulas. So first we are finding the pre-wrapping frequencies, that is angular frequencies, that is one passband frequency and second one is stop band frequency. And then what we are going to do, we are finding the analog transfer function of the analog filter h of s. After finding that, just we are choosing the appropriate answer. T value we are going to choose here. T is equal to 1 second. And finally, whatever the equation we are getting here, instead of s, we are substituting that with 2 by t into 1 minus z inverse by 1 plus z inverse. So after substituting that, this HA of s will be converted into h of z. Okay, by substituting in the place of s 2 by t 1 minus Z inverse by 1 plus Z inverse, so that I am going to get the value H of Z. These are the 4 steps that involves in the bilinear transformation. Let me take one problem. Apply the bilinear transformation. H of S is equal to 2 by S plus 1 into S plus 2. So what is the value? T is equal to 1 second they have given, and he has to convert H of Z, convert analog transfer function into digital transfer function. So first that, what we are going to do, we have taken the analog transfer function of the filter, and our agenda is to convert that analog into digital filter, so that we have already seen in the step, just substituting S in the place of S, 2 by T into 1 minus Z inverse by 1 plus Z inverse, and by substituting all the values T is equal to 1, what we are going to get, this H of S will be converted into H of Z. So that if I am substituted all the values, just see here, substituting S in the place of H of S, I have substituted here and I have substituted here, and by simplifying all the terms, finally the expression what I got. Why? Because here I have also substituted T is equal to 1. Don't be confused. Here the value of T will be equal to 1. So by doing all this simplification, the final expression what I got here is H of Z is equal to this one. H of Z is equal to 0.166 into 1 plus Z inverse whole square by 1 minus 0.33 Z inverse, which it has been perfectly converted into digital filter. So these are some of the steps. These are the steps that involves for the conversion of the bilinear transformation with the for designing the IER filter. I told you here, you can see what we got here. See, we got poles and zeros. If we compare this with the approximation derivative, impulse invariant and impulse invariant, we can see only poles. But here, to overcome the aliasing effect which is present in both top methods which we have seen, the poles and zeros are mapped with the analog poles and zeros are mapped with the digital poles and zeros which is present in the unit S plane as well as Z plane. So by doing that, we can overcome the drawback which is present in the approximation derivatives, that is aliasing effect will be overcome. So this is all about the designing of the IER filter by using some different types of techniques. So that is whatever we have seen in the last lectures, where we have used the Butterworth and Chebyshev filter for the designing of the transfer function of the analog filter. Then after designing that, we have used some 3 different methods which is used to convert the transfer function of the analog filter into digital filters. So this is all about the IER filter in the digital signal processing. Thank you.